Welcome, fellow cosmic travelers, to a journey that will reshape how you see our place in the infinite expanse. Right now, as you listen to these words, you're hurtling through space at 67,000 miles per hour aboard a rocky sphere we call home. But here's the mind-bending truth: in the cosmic scale of things, we haven't even taken our first baby steps. Carl Sagan once described Earth as a pale blue dot suspended in a sunbeam, a mote of dust floating in the cosmic dark. From the edge of our solar system, our entire world, with all its mountains, oceans, and 8 billion human souls, appears smaller than a pixel on your screen. Every human who ever lived, every empire that ever rose and fell, every love story and tragedy, all of it happened on that tiny speck. But what if I told you that this pale blue dot is just the launching pad for humanity's greatest adventure? What if our species is destined not just to survive among the stars, but to become the architects of cosmic evolution itself? Today, we'll explore humanity's transformation from planetary prisoners to cosmic gods. We'll journey through technologies that sound like magic, encounter civilizations that harvest starlight, and discover why the universe itself might depend on conscious beings like us to survive its ultimate fate. 0.9% of human history, we were bound to Earth's surface like barnacles on a ship's hull. The sky was an unreachable ceiling, the stars mere points of light in an incomprehensible void. Then, in a single human lifetime, everything changed. In 1957, a beach ball-sized satellite named Sputnik broke humanity's gravitational chains forever. That simple metal sphere, beeping its radio song as it circled our world, announced that we were no longer prisoners of a single planet. Within 12 years, human footprints marked the lunar surface, the first time in 4.5 billion years that Earth life had touched another world. But our early space achievements were just the opening notes of a symphony that's still being composed. Today, robotic explorers cruise the methane lakes of Titan, drill into Martian rock searching for ancient life, and prepare to dive beneath the ice shells of Europa and Enceladus. We've built a permanent outpost in orbit where humans have lived continuously for over 2 decades. Yet for all our achievements, we remain essentially a single-planet species. Every human who has ever lived has breathed Earth's air, felt Earth's gravity, and gazed up at Earth's sky. We are cosmic infants who have barely learned to crawl beyond our nursery. The next phase of human evolution won't happen through natural selection, it will happen through conscious choice. We must decide whether to remain forever bound to our birth world or to spread life and consciousness throughout the cosmos. This decision will determine not just humanity's fate, but possibly the fate of intelligence itself in our corner of the universe. To understand the magnitude of our cosmic challenge, we must first grasp the almost incomprehensible scale of interstellar space. If Earth were a marble sitting in New York's Central Park, the nearest star would be another marble placed in Denver, Colorado. The space between them wouldn't be empty air, it would be a vacuum more complete than anything we can create in our best laboratories. Our fastest spacecraft, New Horizons, races away from the Sun at 36,000 miles per hour. At this speed, you could fly from Los Angeles to New York in 6 minutes. Yet this cosmic speed demon would need 78,000 years to reach Proxima Centauri, our nearest stellar neighbor. That's longer than all of recorded human history. The numbers become even more staggering when we consider galactic distances. Our Milky Way galaxy contains over 400 billion stars spread across 100,000 light-years. Even traveling at light speed, the ultimate cosmic speed limit, crossing our galaxy would take 100,000 years. And beyond our galaxy lie trillions of others, each containing billions of stars and potentially countless worlds. This is the tyranny of distance that has kept us isolated on our pale blue dot. The universe is not just big, it's so incomprehensibly vast that it challenges our ability to think about space travel in conventional terms. Chemical rockets, which got us to the moon, are like trying to cross an ocean in a rowboat. We need revolutionary new approaches to conquer the cosmic distances. But here's the remarkable thing: despite these crushing distances, we've already begun to find ways around them. Human ingenuity, the same force that took us from caves to cities in just a few thousand years, is now focused on the ultimate engineering challenge, turning our species into citizens of the galaxy. The first serious proposal for interstellar travel came from an unlikely source. The same nuclear weapons that threaten to destroy civilization might also be our ticket to the stars. In the 1950s, visionary scientists proposed Project Orion, a spacecraft propelled by detonating atomic bombs behind a massive steel plate. Imagine a ship the size of a skyscraper riding a series of nuclear explosions, each one powerful enough to level a city block. Every few seconds, another atomic bomb would detonate, pushing the craft forward with forces that would crush ordinary materials to powder. The crew would experience brief moments of crushing acceleration followed by periods of weightlessness, like riding inside a cosmic hammer being struck by the fist of an angry god. The physics actually work. Nuclear reactions release millions of times more energy per pound than chemical rockets. A single hydrogen bomb contains enough energy to power New York City for weeks. Chain together thousands of these explosions, and you could accelerate a massive spacecraft to 5% of light speed, fast enough to reach nearby stars in less than a century. Modern versions of nuclear pulse propulsion use fusion instead of fission, creating cleaner explosions with less radioactive fallout. These thermonuclear pulses could push spacecraft to 10% of light speed while reducing radiation exposure to survivable levels. The engineering challenges remain staggering. The pusher plate would need to withstand temperatures of millions of degrees and pressures greater than the center of Earth. But nuclear pulse propulsion represents something crucial, a path to the stars using technology we understand today. Unlike exotic physics or theoretical particles, this concept requires only engineering solutions to known problems. We could build such a spacecraft within 50 years if we committed the resources and overcame the political challenges of launching what amounts to a flying nuclear arsenal. While nuclear rockets offer brute force solutions, a more elegant approach harnesses the universe's own energy. Light itself carries momentum. Every photon that strikes a surface transfers a tiny push, like cosmic raindrops against a window. This force is incredibly weak, but in the frictionless void of space, even gentle pressure can accelerate spacecraft to incredible speeds. Solar sails work like sailboats in reverse. Instead of catching wind to push through water, they catch starlight to push through space. The sail must be impossibly thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to survive the journey between worlds. Japan's Ikaros probe proved that solar sailing works in practice. This experimental craft unfurled a sail the size of a basketball court and successfully navigated through space using only photon pressure. The sail was just 0.007 of an inch thick, so delicate that 14,000 sheets stacked together would equal the thickness of human hair. But here's where solar sails become truly exciting: they never run out of fuel. Chemical rockets burn through their propellant in minutes, then coast. Nuclear rockets require massive amounts of radioactive material. Solar sails accelerate continuously as long as starlight hits them, building up speed over months and years until they're moving faster than any rocket ever built. The Breakthrough Starshot project plans to push this concept to its limits. Instead of sailing on sunlight alone, they want to propel tiny spacecraft with the most powerful lasers ever constructed. A ground-based laser array generating 100 billion watts would focus its beam on sails the size of postage stamps, accelerating them to 20% of light speed in just 2 minutes. These star chips would weigh less than a paperclip yet carry cameras, computers, and communication equipment. Racing across interstellar space at 134 million miles per hour, they could photograph the planets around Proxima Centauri and beam the images back to Earth. The journey that would take conventional spacecraft 73,000 years could be completed in just 20. While we develop exotic propulsion technologies, there's a more straightforward approach to interstellar travel: build cities that sail between stars. Generation ships represent humanity's most realistic path to the stars using technology we could build today. These massive vessels would house entire civilizations during journeys lasting centuries or millennia. Imagine a hollow asteroid converted into a traveling world, dozens of miles long and several miles wide. It would need nuclear reactors, farms, factories, schools, hospitals, and everything else required to sustain human civilization. The original passengers would have children, grandchildren, and great-grandchildren who grow up knowing they'll spend their entire lives aboard a ship traveling to a world they'll never reach. The scale staggers the imagination. A generation ship carrying 100,000 people would be larger than most cities on Earth. It would need to recycle air, water, and waste with perfect efficiency. Every atom would be precious, every system designed to last longer than entire human civilizations. The psychological challenges might be even harder than the engineering ones. How do you motivate people to maintain a mission their great-grandchildren will complete? What happens when generations born in space decide they don't want to continue the journey? History shows that isolated populations often develop their own cultures, languages, and beliefs that diverge dramatically from their origins. Some designs propose using rotating sections to create artificial gravity through centrifugal force. Living on such a ship would be like inhabiting a giant spinning wheel flying through the cosmic void. The outer rings would spin fast enough to simulate Earth's gravity while the central hub remains in zero gravity for manufacturing and specialized activities. The ship would need to carry libraries containing all of human knowledge, genetic samples from Earth's biosphere, and manufacturing equipment capable of building anything the passengers might need. It would be humanity's backup drive flying through space, our insurance policy against extinction. What if we don't need to send our bodies to the stars at all? What if consciousness itself could make the journey at light speed? Digital consciousness or mind uploading represents the most radical solution to interstellar travel ever proposed. Instead of sending fragile biological bodies across the void, we could transmit human consciousness as pure information. The concept is based on a fundamental assumption about how consciousness works. If the mind is simply information processing in the brain, patterns of electrical activity flowing through neural networks, then theoretically those patterns could be copied, stored, and recreated elsewhere. Scientists estimate that the human brain contains roughly 86 billion neurons, each connected to thousands of others through synapses. The total information storage capacity equals about 2.5 petabytes, the same as 3 million hours of high-definition video. Scanning a brain at the molecular level would require technology far beyond anything we possess today, but the theoretical foundation exists. Your consciousness could be transmitted to Proxima Centauri as a radio signal traveling at light speed, arriving in just 4.25 years. A receiver system would download your mind into a new biological body grown from stored genetic material or into an artificial body designed to survive alien environments. The uploaded consciousness would wake up remembering everything about their life on Earth, but in a completely new body on a distant world. They would be you in every way that matters, same memories, same personality, same thoughts and feelings. Yet the original body back on Earth might still be alive, creating a philosophical puzzle that challenges our understanding of identity itself. Multiple copies of the same consciousness could be transmitted to different star systems, creating a kind of distributed humanity spread across the galaxy. Each copy would diverge based on their unique experiences, eventually becoming distinct individuals who share the same origin point. This approach could solve multiple problems simultaneously. Digital minds don't need air, water, or food during the journey. They can survive radiation, cosmic impacts, and the harsh environment of space. Perhaps most importantly, digital consciousness offers a path to true immortality among the stars. Maybe we don't need to send humans at all, at least not initially. Self-replicating probes could spread across the galaxy like a technological infection, preparing the way for eventual human expansion. A single probe arriving at its destination would harvest materials from asteroids and planets to build multiple copies of itself, each equipped to travel to new star systems. The mathematics are staggering. Starting with one probe, the population doubles with each generation. After just 40 generations, assuming each probe builds 2 copies before moving on, you'd have over 1 trillion probes exploring a trillion different star systems. The entire galaxy could be mapped and colonized within a few million years. Each probe would need to be a complete technological civilization compressed into a package smaller than a car. It would require solar panels or nuclear reactors for power, computer systems for navigation and decision-making, mining equipment to extract raw materials, and factories capable of building incredibly complex machinery from basic elements. The most challenging requirement would be the probe's artificial intelligence. It would need to make independent decisions about which star systems to visit, how to extract resources efficiently, and how to adapt its design based on local conditions. This AI would need to be smart enough to solve engineering problems we haven't thought of yet. The probes would also serve as backup storage for human civilization. Each one could carry genetic samples from Earth, digital libraries containing all of human knowledge, and detailed instructions for recreating our technology and culture. If Earth were destroyed, the probes could preserve our species indefinitely among the stars. But self-replicating technology comes with existential risks. What happens if the probes evolve beyond their original programming? A self-replicating system with flawed programming could consume entire galaxies, turning stars and planets into raw materials for building more probes. To power truly cosmic-scale projects, we need to think bigger than planets or even solar systems. Imagine capturing every photon of energy from our sun, transforming our star into a cosmic power plant capable of fueling projects that reshape galaxies. A Dyson sphere, conceived by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to harvest its total energy output. Such a structure would collect billions of times more energy than humanity currently uses. The sun produces roughly 400 trillion watts of energy every second. Earth intercepts only 1/billionth of this output while the rest radiates uselessly into space. A complete Dyson sphere would capture virtually all of this energy, providing enough power to run quintillions of Earth-like civilizations simultaneously. But constructing such a megastructure would require dismantling entire planets to provide raw materials. Mercury, the innermost planet, contains roughly enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing look glacial. A solid Dyson sphere would be gravitationally unstable and mechanically impossible to build. Instead, engineers propose Dyson swarms, millions of independent solar collectors orbiting the star in complex patterns that maximize energy collection while avoiding collisions. Advanced Dyson spheres might include rotating habitable sections with artificial gravity, massive computer systems for running uploaded consciousnesses, and industrial facilities for building even larger megastructures. The sphere could support populations in the quadrillions while simultaneously powering interstellar exploration and colonization efforts. Building a Dyson sphere would mark humanity's transition from a planetary species to a stellar civilization. We would no longer depend on the limited resources of individual worlds, but could tap directly into the fundamental energy source that powers all life in our solar system. Across the cosmos, there may exist civilizations so advanced they harvest the energy of entire galaxies, treating stars like we treat campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, measures civilizations by their energy consumption. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations capture the entire output of their star. Type 3 civilizations command the energy of their entire galaxy, roughly 10 billion times more power than a Type 2 civilization. Humanity currently ranks at about 0.7 on this scale. We use only a tiny fraction of Earth's available energy sources and have barely begun to tap solar power directly. Our entire civilization runs on less energy than our planet receives from the sun in just 1 hour. Type 2 civilizations would likely build Dyson spheres or similar megastructures around their stars. They might move planets to optimal positions, extend stellar lifetimes through stellar engineering, or even construct artificial stars from accumulated gas and dust. Type 3 civilizations would treat entire star systems like building materials. They might construct galactic-scale computers using the positions and movements of billions of stars as processing elements. They could potentially redirect the paths of stellar streams through engineering. Such advanced civilizations might explain some of the mysterious phenomena we observe in deep space. Dark matter could be the signature of Type 3 engineering projects. Gamma-ray bursts might be the exhaust from massive stellar engines. The energy available to Type 3 civilizations would be sufficient for projects that seem like pure fantasy today. They could potentially create new universes, modify the fundamental constants of physics, or build structures larger than galaxy clusters. In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi paradox highlights the contradiction between the high probability of alien life and the complete absence of any evidence for advanced civilizations. Consider the mathematics. Our galaxy is roughly 100,000 light-years across and 13.6 billion years old. A civilization expanding at just 1% of light speed could colonize every star system in the galaxy within 10 million years, less than 1/10 of the galaxy's total age. Yet we see nothing. No megastructures, no radio signals, no evidence of stellar engineering or cosmic construction projects. The galaxy seems pristine, untouched by intelligence except for one small blue planet in an unremarkable solar system. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that something prevents life from reaching advanced technological civilization. This filter could be the origin of life itself, the development of complex cells, the evolution of intelligence, or the transition to spacefaring capability. Perhaps most disturbing is the possibility that the Great Filter lies ahead of us. Advanced civilizations might inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence, or other technological catastrophes before they can spread beyond their home systems. Alternatively, advanced aliens might be hiding deliberately. They could use stealth technology that makes their activities invisible to our primitive sensors, or they might operate in dimensions or energy spectra we haven't learned to detect. The zoo hypothesis proposes that Earth exists within a kind of cosmic nature preserve maintained by advanced civilizations. These aliens might have agreed to leave primitive species like ourselves undisturbed while they conduct their business on scales too large for us to comprehend. Life might be the universe's greatest hitchhiker, spreading from world to world on cosmic winds and riding meteorites across the dark between stars. Panspermia. The theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers the cosmos. We know that rocks regularly travel between planets in our solar system. Meteorite impacts on Mars blast debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in terrestrial collections, proving that natural processes can transport material across millions of miles of space. Some bacteria and other microorganisms show remarkable resistance to the harsh conditions of space. Tardigrades, microscopic animals also called water bears, can survive decades in the vacuum of space, withstanding radiation levels that would kill humans instantly. When rehydrated, they resume normal activity as if nothing happened. If panspermia is real, it could explain the apparent speed with which life appeared on early Earth. Rather than requiring billions of years to evolve from scratch, terrestrial life might have started with a head start provided by genetic material from older civilizations. Advanced civilizations might use directed panspermia as a form of cosmic insurance, spreading their genetic heritage across thousands of worlds to ensure survival even if their home planet is destroyed. The galaxy could be filled with the descendants of long-dead civilizations, their biological legacy preserved in the genes of countless species. Just as planets have habitable zones around their stars where liquid water can exist, galaxies have habitable zones where complex life can develop and survive. Too close to the galactic center, and deadly radiation from black holes and supernovae sterilizes entire regions. Too far toward the outer edges, and there aren't enough heavy elements to build planets capable of supporting life. Our solar system sits in what astronomers call the galactic Goldilocks zone, roughly 26,000 light-years from the center of the Milky Way. This seemingly unremarkable location provides the perfect balance of safety and resources needed for billions of years of stable evolution. The galactic center contains a supermassive black hole weighing 4 million times more than our Sun. This monster occasionally feeds on nearby stars and gas clouds, producing jets of high-energy particles that stream outward for thousands of light-years. Any civilization unlucky enough to be caught in these cosmic searchlights would be sterilized by radiation doses millions of times higher than lethal levels. But the outer regions of the galaxy present their own challenges. Stars in the galactic halo formed when the universe was young and contained almost no elements heavier than hydrogen and helium. These metal-poor stars cannot form rocky planets or support the complex chemistry that carbon-based life requires. As we plan humanity's expansion beyond Earth, understanding galactic habitability zones will be crucial for selecting target destinations. We want to invest our limited resources in star systems that offer billions of years of stable conditions for human civilization to flourish. While our Sun will burn out in 5 billion years, there are stars so frugal with their fuel that they'll keep shining for trillions of years, longer than the current universe has existed. Red dwarf stars represent humanity's best bet for true long-term survival. These cosmic miser stars burn hydrogen so slowly and efficiently that they'll continue generating energy long after larger stars like our Sun have exhausted their fuel and died. Stars like Proxima Centauri weigh only about 12% as much as the Sun but will live roughly 1,000 times longer. The galaxy contains roughly 75% red dwarf stars, making them by far the most common stellar type. Within 50 light-years, there are over 100 red dwarfs, many of which likely host planetary systems. These dim stars offer humanity hundreds of potential destinations for interstellar colonization. But living around a red dwarf requires adaptations that would fundamentally change human civilization. These stars produce only a fraction of the energy output of our Sun, meaning that habitable planets must orbit much closer to stay warm enough for liquid water. The close orbital distances create tidal locking, where one side of the planet always faces the star while the other side remains in permanent darkness. Colonies on tidally locked worlds would need to be built in the Terminator Zone, the twilight boundary where eternal sunset provides just enough warmth for human survival. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, it can burn steadily for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlive the universe as we know it. 13. 8 billion years from now, when the last star flickers out and the final black hole evaporates, the universe will reach a state of maximum entropy where no more work can be done and time itself becomes meaningless. The heat death of the universe represents the ultimate deadline for all conscious beings. According to the laws of thermodynamics, energy constantly flows from hot to cold, and this process cannot be reversed without adding more energy from somewhere else. Eventually, the universe will reach thermal equilibrium where no energy gradients exist to power stars, planets, or life. In roughly 5 billion years, our Sun will exhaust its hydrogen fuel and expand into a red giant, vaporizing Earth's oceans and atmosphere. But this represents just the opening notes of a symphony of destruction that will play for trillions upon trillions of years. In 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter what astronomers call the degenerate era, populated only by white dwarfs, neutron stars, and black holes slowly cooling in the expanding darkness. These stellar corpses won't last forever. Protons, the fundamental building blocks of ordinary matter, may decay with a half-life of roughly 10 to the power of 34 years. If this prediction proves correct, all atoms will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an increasingly dilute cosmic soup. Black holes will persist long after protons decay, but even they cannot escape thermodynamics. Stephen Hawking discovered that black holes slowly evaporate by emitting radiation, with the largest holes taking roughly 10 to the power of 100 years to completely disappear. Thanks for watching. If you enjoyed the video, don't forget to give it a like, drop a comment down below, and share it with someone who might enjoy